So, yeah, so thanks for being here. And today I've prepared this tutorial. It's pretty rich, so I hope we will manage to get to the end. If we don't, we can, I don't know, either continue next time or we will see it. So, so the motivation for this tool I've developed in collaboration with Gianvito Taneburgo, which is a friend of mine back in Italy and is the other big mind behind the project, is that we wanted to have something very easy to use for researchers to start creating their surrogate model and use it directly to perform uncertainty quantification, in particular global sensitivity analysis. So a lot of libraries existing out there are very powerful, yet they limit the user experience in the sense of training the model itself. And I'll talk about it later on using an example. So let's directly go into a 1D example to show you what I'm talking about. So the aim is to replace this function. We call it simulator, which normally takes an input of d dimensions and gives back a scalar feature as an output. This might be a very complex deterministic model of which we have, for example, some evaluations. And we want to replace this with a surrogate model, which is fast and can predict the output in a hopefully accurate way. But the important thing is that it's fast. And this will enable many things, including global sensitivity analysis studies. So let's start with importing some libraries. Here we provide some functionalities to set the seed in a way that all the libraries that takes into account random algorithms will be set to the same seed. And also we set a logger that which will contain everything at the end of what we run. So here I'm showing a little example. Instead of using the boring sinx, I'm just made a slight modification of it, taking this forcer function. And we immediately import it from test functions here, providing the utils of the library. Now this function, we will call it f for simplicity, and is a function that takes a 1D input and gives back a 1D scalar output. So we define the dimension, and then we use a functionality of GPErks, which creates a dataset out of a function. So this is the case where we have an analytical expression for it, but normally we don't have this function. But now that we have it, we can use it. So we know that this function ranges between 0 and 1, but if this is d-dimensional, the list provided here have to be of length d. And we just ask to create 10 points in the training dataset and 10 points for testing the accuracy of the emulator. We set the seed, and the way in which we build the dataset will be according to a simple random sampling, but this can change. This can be a Lightning Hypercube sampling or a Sobol sampling. I will show you later on, but for the moment, just create the dataset. Okay, so the Gaussian Process Emulator that we use is gonna made of a sum of two parts. The first part is a deterministic part, is given by a linear regression model, and the second part will be a stochastic process, in particular a Gaussian process, since this is a GP emulator, and I will be using the squared exponential kernel as a covariance function. This is very easy, and the first choice you can make selecting kernels. And then the likelihood, we will define the output to be affected by noise. Now, you would say this is a deterministic function and doesn't need to be modeled as a noisy observation. However, adding these terms helps when the covariance matrix will have to be inverted. So having a noise fitted will help according to numerical stability. So what we do is really everything is built on Torch, in particular on GPyTorch. So this API was built on top of GPyTorch. And so every element to build the emulator will be taken from there. So, and it can be changed, of course. So now we define a likelihood. We take it from GPyTorch, and we define it to be the simplest. So the Gaussian likelihood here. And then we define the mean function, and we take it to be a linear mean, so the mean that I showed here. With the input sides, of course, dataset we start building its own attributes according to what you passed in. So you passed a d equal to 1 here, so the input sides now will be 1. And then we choose the covariance function, which is the kernel, and we scale the RBF kernel to have an additional hyperparameter in front of it. And we implement automatic relevance determination, meaning that this kernel will have a number of length scales, which is equal to the number of input features. In this case, still 1. Okay, so I'm not running this, but I should run this. And then for matrices, we depend on a third-party library. It's called Torch Metrics. So you can import as many metrics as you want to be monitored, and you just include them in this list. So for example, I'm providing a mean square error and R2 score, just because these are very common and everybody knows what they are. But I think Torch Metrics includes more than 20 possible metrics for regression and other 10 for classification, I guess. So the next thing is to define the experiment. So here we instantiate this class called GPE experiment. And this experiment takes as an input the dataset that we built, the likelihood function and the mean function and the kernel that we chose, and then the matrix vector that we define, the seed, of course, we want to reproduce the training. Learn noise means that we are actually learning this parameter that I showed before, but you can also switch this to false, although I wouldn't recommend to do that because of the numerical stability issue I talked to you about. And the restarts is just a way of telling how many times we want to restart the optimization problem, starting from a different point in the hyperparameter space. In order to not get stuck in local minima, we might want to restart this more than once. The default is, I think, 10, but here, just to speed up things, I'm doing 3 restarts. So after we define the experiment, we just select the device. This is just a shortcut when you have a GPU available. This code can be run on GPU, also on CPU. But here, I think everything will run in CPU because I don't have a GPU in this laptop. And then we define the optimizer. This is just one of the optimizers I chose from Torch. Optimizers available it implements a stochastic gradient descent algorithm, and it's pretty cheap in terms of memory consumption, and it's pretty reliable. So normally one would go with this. The learning rate, I'm fixing it to 0.1, but you can implement also dynamic learning rate, such that you can scale this according to how the optimization is doing during epochs of training. And so after you define the device and the optimizer, now it's time to define the emulator itself. And the emulator itself takes as an input the experiment that we define above and the device on which we want to send the model. And then we can call the train, providing the optimizer. So we run the first training, and you can see that this is going. So here it provides the training loss at a specific epoch, and it provides the monitored quantities that you ask in the matrix vector, still computed on the training dataset. This is because we didn't provide any validation set. So here it's just running all of them up to 100, which is a default value of max epochs to run. And at the end, you will see that we have evaluated 3 restarts. The best restart happened to be the second. And since the training loss is always decaying, unless this is a very unstable problem, the best epoch, of course, will be taken to be, in this case, the last one, because it's the lowest value we reached with the training loss. And eventually what you will see is the set of fitted hyperparameters of the GP. So when you say I'm training a GP, this means I'm fitting hyperparameters such that these will represent the data on which I'm training the GP on. And so the bias will be the beta 0 of the mean vector, the weights of the mean function. The weights, in this case, is just one weight, beta 1, because the input is one-dimensional. And the output scale is the scalar in front of the kernel that we use. Length scale, we just have one length scale. because the kernel is still 1D, and the likelihood noise, you can see that the noise is pretty small. So even if we trained an output to take into account that it is noisy, this happened to be fitted with a very small value, means there is no noise. In fact, we are using a deterministic function, the Forrester 1D example I showed you before. So let's dive into inference. We have the testing set that we defined at the start. So this is inside dataset object. The first thing we can do is to predict to see how the emulator is performing on a test set. So we just call the predict function. This will return a mean vector and a standard deviation. So this is the mean from the posterior distribution of the trained GPE, and this is the uncertainty around the mean. So we can iterate over the matrix vector, but since these are from torch metrics, what it takes as an input should be tensorized, so it should be a torch tensor. So we tensorize the NumPy and the array that we get. So this is the predicted mean, while this is the true mean. So it means the true value that we have evaluated using the Forrester function. And we can compute this. So the MSE is this value, and the R2 score is this value. But we have automatic inference tools. So the first perk I show you is the inference one, which directly takes the emulator as an input and gives you a summary. And the summary is actually what we just calculated here. So it takes all the matrices and it evaluates them against the testing set that it's within emulator, because emulator has got experiment within it, experiment has got dataset within it, and dataset has got X-test within it. So using this, we can retrieve all we've done here in one command, and this is good to have. Also, this can be retrieved, I think, from this inference scores. If you want to use these scores for some reason elsewhere, you have the full dictionary stored within scores dict. And what we can do now is to plot. So here I just made the plotting function. So what we do is we retrieve the training dataset that was built inside dataset, and then we make a huge lin space between the bounds of the X. So I want to predict 1,000 points. So I predict them all, and I obtain a mean function standard deviation around it. But also I have true values for that, because I can use the F to evaluate this lin space in it. So I can plot all of it, both the predicted mean and the true mean, and the standard deviation, and also the points we use for training. So you can see that we have the full dots are the training points, and then the predicted mean is the continuous full line, and then we have the dashed line is the true value, the true function, the Forrester function, and also the STD I've plotted two standard deviations, so it's approximately 95 confidence interval around it. So you can see that the confidence interval become very small around regions where we know a lot of the function, so where we have train points here. And in between, for example, from this train point to this other train point, the confidence interval is bigger because there's no information here. And also if we try to extrapolate, so on the left border after this training point, you see that the uncertainty grows even more. In fact, here there is a mismatch between the true value and the predicted value. Also, inference has a plotting functionality in which this is very handy. It doesn't show any X, because normally you can use this for a high dimensional input. But what I've done is to basically sort in ascending order all the mean values, so the predicted values, and sorting accordingly the open dots, which are the observations, so the true values. And this can make you realize how the training is doing, in the sense how the inference is doing, in the sense of if the testing points are still within the uncertainty predicted by the emulator or not, or if they are matching, like for example in this case they are pretty overlapped. But also we cannot, before we use predict, and this gives back the size of this vector is 10 because we had 10 test points. But we can also use the sample function to directly draw samples from the posterior distribution. And in this case, the matrix, here you decide how many points you want to draw, so how many samples you want to draw. And this will be given in a matrix of, every sample will be in the row of this matrix. Of course, this is will be computed at each test point, so for 10 points. And I can plot them as well. This is how samples look like. So we have the training data is still the black dots. And then we have the posterior mean, which is, before it was illustrated with the full line. And then the samples are all them, so all the colored one. And this is taking into account the uncertainty as well. So we're just drawing samples from the posterior distribution. Okay, so this was the 1D example. Let's directly move into the 2D to show other functionalities as well. For the 2D example, I chose another function which is normally used for benchmark. It's called current function. Of course, this is 2D. So I've just made this function to be evaluated in each row of the matrix X, just to be sure that eventually I will get a vector for each row of the matrix. D will be equal to 2. And again, we create a data set. This time I'm going to use a Lightning Hypercube sampling. I didn't show you before, but actually dataset implements plot functions. So with the plot, you can actually plot what you got from the function. So the first parameter, input parameter versus the output, and the second parameter versus the output. Here we chose, here I'm plotting the training set. And here I can plot also parameters versus themselves. So here you can see the distribution of the sampling strategy we are using. Now, this is a Lightning Hypercube sampling, but there are too few points you cannot appreciate. Let's put, I don't know, 500. You can see that the pairwise gives you a space which is very uniform in the 0, 1 times 0, 1 two-dimensional space. We can change this. We can also use a Sobol. This will give you another structure. You can see different kind of strategies of sampling. But for the moment, let's just keep it with few points because it takes less time to be simulated. And yeah, so this is the space and can be shown. But for what concerns the rest is exactly as before. We define the likelihood, we define the mean function, the kernel, metrics, and then we define the experiment again, optimizer, device, all the stuff that we saw before. Nothing really changes. So we start. The training will proceed, and you will get now fitted hyperparameters. You see that the beta weights are now 2, so beta 1, beta 2, along with beta 0 of the mean function, and also length scale will be 2 instead of 1. And we can perform inference. So this is the scores, and this is what I showed before. There is one prediction which is off. Actually, I think there are two, even this one a bit. But overall, this is a very good accuracy over the testing set. But one thing we can do is to interpolate an entire 2D grid. This is cool to have because we have a 2D function and can be plotted very nicely. So I just made a grid and I asked the emulator to be evaluated in the grid. And this is the posterior mean. And this is the standard deviation we get at each point of this grid. But the cool thing is that since we have an analytic function f, which is the current, we can use it. And this will give the true value in this grid, and we can compare them. And we can also plot the relative error between the two. And this is basically showing what I showed you before. So when we have information, the relative error will be smaller. In fact, the information accumulates in the darkest region of this error. So everything here is pretty consistent with the 1D example. But of course, in 3D, it will be, I think, a bit trickier to display it. Anyway, this is the the common principle behind emulation. Where you have data, of course, the emulator is more accurate. And secondly, we can use a set of diagnostics to understand if this emulator is actually a good representation of the model, and not only for inference purposes, but if we want to do, for example, GSA, global sensitivity analysis, we need to have an emulator which can be trusted in terms of a set of diagnostics. So what I've done is to take a set of diagnostics here from O'Hagan paper, and I think this will apply in our case, but even more in general. And these diagnostics are evaluated using the covariance matrix. So I didn't show you before, but if you set with covar equal to true, when you predict a test point, you also get covariance matrix as an output. So this is a 25 times 25 matrix. It's a square matrix, and it has the same size of the training dataset. So the training dataset was 25 points. And yeah, I can also display it here. You can see that this is the covariance matrix as an heat map. You can see that the higher correlations are on the diagonal, and as far as the points are far apart themselves, the covariance between them will decay. And this is because of the kernel we chose, which is a squared exponential kernel. And I think we can retrieve it from the first tutorial. The squared exponential kernel was decaying according to the distance. So that's why outside the diagonal, you have lower values of the covariance. And what in the diagnostic, you can still print a summary. And this will give a set of measures. The first one is a chi-squared distribution of independent standard errors, where independent standard errors, I mean the difference between the mean that you get minus the true value divided by the standard deviation, and that is called independent standard error. So this distribution should be following a chi-squared, and so you have both the theoretical values and the value that you get from your emulator. So this is not perfectly overlapping with the expected mean, but we also have a pretty high standard deviation. So overall, it's not a bad measure, I would say. The Mahalanobis distance is another matrix that can be computed, and that is taking into account the fact that we can use the covariance matrix that we obtain here and multiply it with the difference between the true value and the predicted value. And that also has to be distributed with a certain distribution, which is an F distribution, and as this with theoretical expected value and standard deviation. This is the predicted. And also we have the credible interval, which is how many times we manage to fall within two standard deviations. And in fact, you saw before that we have 25 points and only 2 of them are out. So this actually gives you the 92 of credible interval you see here, means that 92% of the points were predicted to be within the uncertainty given by the emulator. And also the diagnostic can be plotted. In particular, you can plot the uncorrelated diagnostics, which are basically the predicted, the posterior mean of the emulator against this measure called DG. For details, I think I recommend you to look at this paper. But what can you do to understand it better is to plot the uncorrelated ones, because these are more interpretable in the sense of standard error. This is what I displayed before. So basically 2 points are out of 2 standard deviations. And also we plot the same points against the theoretical quantile to see if they are not following any distribution, but they are like a normal distribution. So the errors distribute as a normal distribution. So yeah, I think this is good to have in conjunction with the inference. So in conjunction with inference, I think they should be used together every time we want to use this emulator to perform something more than just accuracy plots. I mean, if you want to just plot accuracy plots, it's okay using the inference by itself. But if you want to use the emulator as a practical tool for doing something more complicated and where you need to trust it 100%, it's better to look at diagnostics as well. So, okay, so let's move into the third tutorial. This is about the handling of input-output. And here I wanted to talk about how you deal with models and all these things we have seen so far, how you can load and save. So I'm just using the same function as before. Here I go quick, is really a copy-paste of the previous thing. Now, one thing you can do is to dump the entire experiment into a config file. Here I'm calling with the name of the example ini. When you run it, this will give you some warnings. This is because we cannot really save and dump everything. If you think about it, every element of this experiment comes from a GPyTorch element. But in GPyTorch, what you can do is you can define additional constraint on parameters. You can define prior distribution on hyperparameters. So all these things cannot be really dumped into a file. So what we decided is to dump the skeleton of the experiment. So now that I've run this, we can go here. It appeared here, example 3 ini. We can look at the skeleton. So number of restarts, the seed we used, we learned the noise, the metrics. This is going to be expanded according to how many metrics you will use, the likelihood that you used from GPyTorch, the mean function, and the input size of the dataset we had, and the kernel. I think this is a minimal number of things you need to know to reproduce your experiment. But of course, if you have added other arguments that are more tricky and complex, this cannot be dumped in this file. So yeah, this is everything. And then we can of course delete the experiment variable that we create before, and we can load it from the config file that we just created. Of course, you still need to provide the dataset. So to recreate the experiment, you need the dataset, and we didn't dump it, of course, because dataset can be arbitrarily large, and we don't want to waste memory. So if you remember to have your dataset stored somewhere, and you want to repeat with the same experiment, you just load the config file, and then you provide the dataset that you have used. So here we are loading the experiment. Still, we decide the device and the optimizer. And then here we define the emulator. And here, before really training, I wanted to show something else. Now, so far we have used snapshotting of the models that we have created in a very automatic way. But actually, a snapshotting criterion can be provided during training here. And we can define how we want to really save our model. So here we provided three snapshot criteria, which save at every epoch of the every n epoch of the training, or save at every epoch, or never save. Of course, this will still create a symbolic link to the best model because we want to retrieve the best model. So I didn't tell you before, but while we were training example, the first two notebooks, this folder was created. And what we can see is that we have two folders. I mean, the first thing we can see is that it took me like 20 minutes to go from the first tutorial to the second, but this is the first tutorial. So when we trained the 1D example, and you can see you have a folder for each restart you made. And by default, this saved a model every 5 epochs. This is just a default choice to save memory, but default could be never save, or default could be save every epoch. And this is the second tutorial of the 2D case. Still, you will have a symbolic link to the best model out of the 3 restarts. Now, I don't remember if it was the second or restart 3, but basically this will link to one of these. And yeah, so what you can do is you can customize the way in which you are saving. So how you customize? You need to define the snapshot directory. And here we just we already have the snapshot folder. We just append example 3 folder. And then you need to define a template for saving. So the first template should refer to the restart, should always contain the restart string. And the template for saving the epoch should always contain the string epoch here. And then what you can do is to train using the snapshot criteria you just define. This is running the training again. And what you can see is that in the snapshot, of course, the example 3 just created. This is again with 3 restarts, but now I've used every epoch. So you can see every epoch you have a saved file, so up to 100. Okay, so this is how you customize the saving of the models. But also, one thing I wanted to show is that, okay, yeah, here we can perform inference, whatever. And what you can do is to load now a model. So you can append best model flag to the snapshot dir that you have created, because best model will always be created no matter the criterion you use for snapshotting. And this actually is not an object, but it's a dictionary of trained hyperparameters. This is because to really save a model, you just need to save the key of the hyperparameter, for example, length scale or output scale or bias, and the value that was fitted at the end of the training. So how you load the model, you just select the dictionary of fitted hyperparameters, and you use the torch load function. With a location, this should be mapped on the current device. This should be included because it might be that someone trained a PTH model on GPU, but if you are on CPU, like in my case here with my laptop, I need to map that trained model on GPU to be into the current device. And so this will give you a state model now that can be loaded into the model of the emulator. So the emulator includes many things, and one of the things is the model, which takes into account everything, the mean function, covariant function, kernel that we define. And you need to load the state of this model using the state that we have just loaded using Torch. So we can just do it. And you can see that all the keys match successfully. So it means that it recognizes every element that you are loading. And then we can perform inference. Of course, the result is the same that you got before, because we are loading the best model, and this was the best model performing inference. So yeah, this is how to really snapshot models in many different ways, and how to load a trained model. Once you load the model here, you can do everything with the emulator object, whatever thing you want that we saw before. Yeah, so the first part is about training stats and loss monitoring and early stopping. I think this is the most crucial part of the tutorial, and I will tell you why later on. So still we import Torch, we import NumPy, we set the logger, we set the seed. So now I'm finally loading a dataset. I'm not computing a dataset using a deterministic function, but I'm just loading this dataset that was built from a real physics problem. Is about this reflectance of plant canopy. And this dataset has got 5 dimensions as an input. And the first thing I'm doing is to generate out of this dataset a training, a validation, and a testing set. So the strategy I'm using here makes use of the scikit-learn package, function called train test split. The first thing I do is to split the entire dataset into something and a testing set. This is because I want to have a testing set to be 20% of the entire dataset. Then we can split what is left. So the 80% of what is left here, we can split it into actual training and validation. Now the validation will be used for help the training process. But first, let's load the labels of these parameters because we know the names. And this is just one label because we are training a single output, a scalar. So this is the canopy reflectance I told you before. And these are 5 parameters of this model, which I really don't know what they are, but yeah, they are called like that. So let's keep on doing this dataset. And we can now build the dataset starting from the generated train, generated val, and test. You can see that these are all optional. You can also not put them, and in that case, there will be just none. But of course, to train, you need a training dataset. And this is what I've done so far. And also you can plug in the labels we have, because at the end we can see the parameters that are playing and the output name. And so this is a case in which you can build a dataset starting from real matrices and not starting from an analytic function as we saw before. And we can plot it, of course. Our string is not defined. Yeah, I didn't run this guy, I think. Yeah, we can plot this dataset. This is 160 points. And whoever built this dataset, I think he did the right job, because also the parameter space is well distributed in the 5D space. Okay, so here we define everything together. Instead of going cell by cell, we saw it before, we just provide the dataset here, as always. And the first thing that changes here, you see that once I train the model, actually I can return something. And what I return here is the best model, which is that can be loaded or can be used somewhere else, and also the best train stats. So the train stats is how losses and matrices that you decided to monitor went over time. So when I mean time, I mean over epochs. So here we define the experiment and we define the model. Here I'm still training 3 restarts. You can see that the difference is that you don't only have the train loss information. Before we stopped here, now you also have the validation loss and the matrix computed on the val set. And so this is good to have, because we can monitor how he went during time. These are the fitted parameters. Now you have 5 betas and you have 5 length scales. And then you can plot the best stats. This plot automatically updates according to the matrices that you have used. Of course, if you put a lot of matrices, this is become very messy. But in this case, we just have MSC and R2 score. So you can see that this is the training we have performed over epochs, and we stopped at the number 100. And yeah, so here you have both the training and the val. We can perform inference. And this is the plot I showed you before many times. And also we can display the criterion used while performing the training. Now, you didn't know this because the criterion used was a default one. In fact, every time I was stopping at epoch 100, but stopping at epoch 100 means nothing, because you cannot ensure that you have actually reached a minima of the log marginal likelihood, which is the loss function in this Gaussian process problem. And so what you can do is to plot the criterion used to stop. So the criterion now is flat, because we didn't use really any criterion. We just said, okay, run up to the epoch 100, and that's what I have done so far. In fact, the best epoch is the 100, because it's the lowest reach point, both for the val and the train loss. So here comes I think the most interesting part of this library, and the motivation for really developing this tool was that almost all the library out there that do GP Gaussian process trainings, at a certain point, they just call this train function, and it does everything underneath for you without any control or on losses, on functions, on anything. So you just hope that train function will reach a minima, and you cannot control that. In this case, instead, we are making full use of GPyTorch functionality. So why GPyTorch is interesting with respect to the other libraries? This is because GPyTorch makes you train a Gaussian process as it were another whichever machine learning algorithm. So if you are training a neural network, you run epochs, you write by hand the training loop. And by writing by hand the training loop, you really have full control of everything. But of course, this comes with some difficulties. So, we have great powers, but, with some responsibilities. And in fact, we need to decide when to stop. And when to stop is not really a trivial task to do. So here I could decide, for example, to use a no early stopping and stop at the 5th epoch. This can be defined in this way. So you just define the max epoch and you train again. You will see that this training now will stop at epoch 50. And of course, I can plot the same thing as before. Here I stopped at epoch 50 instead of 100, but still we cannot ensure that I really reached a region where I'm happy with the training. So we have implemented also some methods from this very cool paper on early stopping, but when. So it's important to know when to stop. And here I've implemented these 3 early stopping criterion that, of course, make use of the validation set. So you will see that all the stopping criterion make use of some information that you have on the val set. But you can also build your custom early stopper by making use of whichever metrics you want to extract from this plot. So you can make an early stopper that takes into account both the training and the val. You can make an early stopper that takes into account the training only or the val only. And for example, the PQ makes use of both. The UP makes use of the sign of this variation, local variation of the val. And the GL makes use of the val only. But in general, you have many flags that can be added to these methods. And maybe I can show you a skeleton later on how to build your custom stopper. It's not simple, but it's pretty efficient once you understand how to build it. And here I'm just showing the GL functionality. This makes use of an alpha parameter, still a max epoch, sorry, because basically if you don't stop, you need to stop somehow. So we still provide an ending point to the training loop. But also, we define an alpha parameter, which takes into account the relative difference in absolute value of the validation loss epoch by epoch, according to the best so far obtained loss. And the patience is just a level of saying, okay, I want to wait up to 8 epochs until I lose my patient and I stop the training. So here, I show you how it works. So you see that the max epochs is 1,000, but we will never reach them because the early stopper will be triggered at some point. So let's see, this is the first epoch. Is running 100 something, yeah. So here it only run 208 epochs out of 1,000, and the second restart is starting. But normally, if the early stopping correctly works, you will never reach the maximum that you gave unless you gave a very small maximum, or unless the model really hasn't learned anything so far and needs more epochs. At least with these small problems, I never run more than 1,000 epochs. If I run more than this, means there was a problem. So this is what I obtain again. And we can plot now the early stopping criterion overlap to the epochs. And you can see the criterion, how it behaves. So here there are some peaks, but fortunately my patient was 8. So I managed to go beyond this curve. Otherwise, the stopper would have stopped early. And maybe I wouldn't have reached this flat part of the valve. Here still I have some patient here as well, but here I went beyond 8 of level of patients, and the early stopper said, okay, you need to stop here. So in this case, the early stopper helped, but this is because we had a validation set, and the validation set, in fact, is used just for this, to help training. But what can we do if we don't have a validation set? Because sometimes we have really few points from our simulator. And it's difficult to have a lot of points to split in test, val, whatever. So we also made this stopper that only use the training data set. So only uses the blue line. In this case, it's called the PK stopper. And in this case, you evaluate the average loss that you get in a strip, in this case of length 20, so 20 epochs. You still have a patient, and the alpha instead works in the contrary. You want to be below the alpha to not for too many epochs, in particular not for more than this, otherwise we stop. So in this case, we already created a data set, and inside the emulator was set with different flags. In particular, there is this scale data set, because everything inside is scaled and then back transform. But in particular, when you provide the validation set, eventually you will have this flag set to true. In this case, we want to pretend we don't have a validation set. So we set this to false. And then still we provide the early stopper that we define here. And we can run this guy now. So again, the validation part is disappeared. So it thinks that there is only a training data set. So we will only see the training loss. But still, this will stop according to the shape, in this case, of the loss. And I will show you at the end how this went. So here we only have training. And this is the criterion that we use. It's called PK. The PK basically interprets when you identifies when you have flat regions, and it stops. Of course, having flat region in the loss or in the training loss doesn't ensure that you have reached a global maxima or a global minima of the log likelihood function of the loss function, but it's true that overfitting doesn't happen before flat regions. So if you happen to be in a flat region, at whichever point you might start overfitting. And so when you are in a flat region, if you decrease the alpha, you want to be really flat, almost zero level of the alpha. But if you set 0.01 like I did, you stop almost immediately, but you can stop even later on. That is your choice. And yeah, the only thing that needs to, as a take-home message, is that really this can be customized in many different ways, but it's important to understand and to evaluate many metrics, the losses over many epochs to understand how your training is doing. For example, you can also do it by hand. You see, okay, I have a flat region here, I want to stop. You just use the no-stop criterion with max epochs, this epoch. So you can really play around with the training in many different ways. All right, so I think we can move to the next one. And here comes the cool part. We can start doing some cross-validation using the emulators. There will be a first part talking about cross-validation, which is the common definition that people think about when they think about cross-validation, and then I will show you a way of using cross-validation for doing a sort of advanced training. So we can start with this one. Yeah, again, we start with common things. Here I'm importing the dataset of the canopy reflectance that we saw before, but really few points, I think half, because there were 160. I'm just loading less points to speed up the process. And here what I'm doing is to split this dataset now into X and XVal. So here I just made a small table to make you understand what I mean by that. Why did I put the quotes in validation? This is because normally when people talk about cross-validation, they mean cross-testing for me. This is because you normally use cross-validation to assess the accuracy of your model, of your trained model, in this case of your GPE, onto different parts of your same dataset. The problem here is that if you talk about validation, you talk about something that helps training. So what you want to do is you want to assess your accuracy on a left-out dataset, which is a part that you don't see during the training, and possibly you can help training using a validation, which is something that we take out at the start. Oh, sorry, but you don't really use this left-out dataset to help the training. You just use it for performing inference. So that's why here I'm putting cross-validation in quotes, because for me this is a cross-testing. We split in 5, in this case, a 5-fold cross-validation. We use 4/5 to train the model, and we assess the accuracy onto the 1/5, which is left out. And then we rotate these splits, and we obtain a score for each of the left-out parts. And then we evaluate the average score obtained into the splits. Possibly we can have a val, like in this case, which we really put out from the beginning, and that won't be used to assess accuracy. So here, what I'm doing is to create a dataset. Again, I put the flags only for the val and not for the test, because now X will be, and then Y will be split in 5. So this is really something which is outside helping the training. I think I run this, yes. And here, as before, we define everything. 3 restart to be quick. And what changes is about the training now. We define the device, but also we can define a list of devices. This is because we can run the cross-validation to be in parallel. And this is, if you provide, for example, a GPU and another GPU, you just provide 2 devices. This will cycle over the same device that you have provided, such that you can fill up all the required folds to be run. So if I run 5-fold cross-validation and I only have 2 devices, that will be used in a cycle. So the first 2, and then the first 2 repeated, and then the first one. Here in this case, I have only CPU. So for every fold, I will repeat the same CPU device. And the splits give you how many folds you want to split the dataset, pretty easy. And the workers is just if you want to run this in parallel or not. Now I will run it sequential. So as we weren't doing anything in parallel, just one CPU. And yeah, so this is the class to implement it. And for the rest, everything is the same. You call the train as you were calling the train on an emulator object. The only difference is that now the train is on a K4 cross-val object. You provide the optimizer, you can provide the snapshotting as before. Here I'm providing the early stopper, otherwise it will take ages. The early stopper I'm using is the GL again. And the only thing different is that instead of returning just 2 things, best model and best train stats, I also return a test scores dict. And this is because we want to monitor, of course, the score obtained over the splits. So if I run this, yeah, so as always, you have the restarts, but now the restarts will be performed for every fold. So here I'm doing 3 restarts for 5. I'm doing 15 trainings, basically. Now they are very sequential and ordered, but of course, if you run this in parallel, every log will be overlapping and messed up. You cannot really follow it. Okay, it's finished, and it provided the score for every split, but let's have a look at them here, because here I'm just using the return test score dict, and I'm doing a mean, so I'm computing the average that matrix had over all the splits. In this case, we have a pretty high average to score, pretty low MSC, so I think this emulator was very accurate in every fold. And what you need to understand is that what we used to help the training was the validation set that was held out from the beginning. So that validation set was always the same. Here you have 5. You see that they behave pretty similarly because they are testing over the same val. What is changing is just the fold, so the points you are using for training. And these are the different splits, the best train stats of all the splits. You can see that the GL is pretty strict. As soon as you start increasing, it immediately breaks and stops the training. But it can do many weird things according to the early stopper that we use. Okay, so this is pretty much it. It doesn't really require many things that we haven't seen before. It's only about defining the class. And running it. Nothing more difficult than that. Of course, you will. Yeah, something I didn't tell is that in the snapshot. So it's this guy here. You can see that in the snapshot we only had restarts because this was 1/4. But for cross validation, the snapshot will contain another folder which is the split. So every split will contain the restarts, and every restart, of course, will contain the model. Here, the default for cross-validation is only best model, so never saved, in the sense that it only saves the best model. And this is because if we do a lot of folds, a lot of restarts, it fills the memory immediately. I mean, these are very lightweight objects, but still it's better not to save every epoch for every split. Sorry, here. Yeah, every epoch for every split, for every restart, it will take a lot. So we just save the best epoch. Yeah, okay, so this was the classic cross-validation. And when I mean classic, I mean cross-validation used for assessing the average score of your emulator. But the issue comes when you don't have many points. And we have seen this many times, for example, with Cristobal dataset or Elias dataset, really with big problems and complex models, you cannot afford having a lot of points, simulated points, to split that dataset into train, test, val. So I thought about a method to train an emulator when you have few points by making use of cross-validation. And so this is what I wanted to show you in this advanced training. This is really simple, and it makes use of the fact that you can split the dataset in a meaningful way. So again, we enforce reproducibility, and we load the same dataset. Now I'm just loading 50 points, but I will split this into tests. Now I'm not contradicting myself. I don't want to use this X test. I just want to use this at the end as a demonstration, but really what I will use, it will be just X and Y. So imagine that I'm cutting half. So imagine that I'm training now with only 25 points, which for a space of 5D, so 5 dimensions, it's really a few number of points. Normally you would want to have at least 10 times the number of input features. So here I'm training with half of it. Instead of 50 points, I'm training with 25. So what I do is to split this and create the dataset. As I told you, I don't provide the test for the moment. I just provide X and Y. This is 25 points. And what I want to do is to perform a cross-validation, but with a flag. So the flag that I'm using is the following. It's called left out is val. So here what I'm doing is really what the word suggests. So cross-validation, I'm really using the left out part to be a validation set, not a testing set. And in this case, why I do that is because since I have few points, I want to make sure that every time I use the left out part to stop immediately the training on the left on the main part of the training, so on the 4/5 in this case, and to give me which was the best epoch, such that eventually I can use the best epoch quantity to have an average best epoch to stop. So let's do it. Here again, cross-validation, 3 restarts for every split. At the end, you will still get a score, but we can ignore it because it's a score obtained on a validation set, but the validation set helped the training, so it's kind of cheating, evaluating the scores on a val set, because in a way that was being used for training. Yeah, so it's finished. We can check at the scores that we obtain, but these scores are now the fake one because these are evaluated on the validation set. So I just print them here, but they are not really meaningful. But the cool thing is that we can now first plot the best epochs obtained when stopping the training, when training on 20 points against 5 points, because that was a 5-fold on 25 points. You can see that sometimes you stop very early. So here you will never gonna learn this function, and it immediately stops. At the end, you can see the best epoch obtained in each split. So the best epoch, of course, according to the criterion used. And why I say advanced training, because now we can use this information. I mean, we can decide how to use it. A way will be, I don't know, if we spot that there is this value, which is a bit odd, we might want to remove it, or just keep it. We want to make use of this information. So how did I do that? You can choose, okay, let's train now on the entire dataset, because we have few points, so we want to use all of them, so all the 25 dataset. Now we provide the test dataset, and we stop at an epoch, which can be, I don't know, a mean, so an average of the best epochs obtained so far, or it can be a minimum, but I wouldn't recommend because the minimum is 3, or at the maximum epoch, so 106. We can really use this information as we want, but I think that the mean value will be a good choice for the moment, and also a recommended choice according to guidelines that I found. And what you do, so you define the emulator. This time we are not doing cross-validation anymore. We just did it for getting out these values. And what we do is to set the optimizer and to set the max epoch to be the mean of the vector of the best epochs. So we are making really use of the knowledge we acquired from the cross-validation. And the early stopper will be no stop, and reach max epochs will be, which will be the given by the mean. And so we can run this guy, and yeah, of course, this will stop to the mean. The mean in this case was 61. It will do 3 restarts as always. Yeah, so this is reaching the end. Let's check the criterion. We don't have any criterion because, of course, we use a no stop. And so we just stopped at the end of the 61st epoch. And also we don't have a val because we had only a few points. So the only thing we can monitor is really the training. But actually the training looked to have gone pretty down. I mean, it's not in the flat region yet. So maybe 60, taking the mean might not have been so meaningful. But we had also that epoch 3 that we could remove to increase the mean value. But the interesting thing is that I've noticed is that, yeah, the uncertainty are a bit bigger, but the scores overall are pretty good. If you think about that this model was just trained on 25 points, and it's a 5D space, I think this is pretty good. And the only way I could achieve that was thanks to the fact that I knew when to stop, even if I didn't have a validation set, because I created my val set by randomly splitting in 5 the dataset. So yeah, this is the end of this notebook. Yeah, so the only thing left, I think, it's about how to use emulators now to perform global sensitivity analysis. Yeah, which is the 7th notebook. So here I'm starting directly with the test function that on which we know analytical solution of sensitivity indexes. How do we want to characterize the global sensitivity of the model? In this case, we decided to use Sobol indices, which are characterized to be main effects, so how a parameter affects the total variance of the output by itself, or total effects. So how a parameter, in conjunction with all the other parameters, up to the highest d-dimensional order of interaction, can affect the total variance of the output. But also second-order effects, this can be estimated, and they represent the interaction of every combination of every pair of parameters in the model. So I chose this function because this is can be expanded to any dimension, and in this case I'm using d equal to 8 to keep things not explode. Well, how do you define this function is by providing this alpha and these delta parameters. Delta are just random numbers between 0 and 1, and alpha, in this case, I'm putting them to be everything equal to 1. But what's important about this function is the A parameters, because the A parameters gives the relative importance of the parameter according to how big is this parameter. So from 0, we have the highest importance. So it works the vice versa. So if you have a low number, it's important. If the number is high, it's less important. And so we can start from 0 up to 99. And this gives importance for the first parameter, less important the second, and so forth. And equally important the last 4. Here again, I'm defining the function to be the Sobol G star that we can import from test functions. And I'm defining the lower and upper bounds of this to be 0 to 1, because this function lives in 0, 1 to the power of d. So in this case, in 8-dimensional space, in the unit cube. And the cool thing is that, as I told you, we have analytical solutions for the sensitivity indices. So I provide them here as well, and we can print them. So you can see the analytic solutions of these indices. So this means that the first parameter has a total effect of 0.78 into affecting the total variance of the output. First order index 71. This is correct because the first order index should be lower than the total effect. Actually, the first order plus second order plus all the higher order should be less or equal than STI, the total, because of its definition. And then we have all the second order effects. This is pretty verbose, but yeah, all the pairs of 8 parameters. You can see that these are still analytical solutions, so true values for these indexes. And you can see that the effects for the last 4 are the same, because they had the same alpha parameter. So by changing alpha, you can really control how the analytic solution should look like. And what we can do is to create a data set to emulate to make an emulator on it. So in this case, I'm using a bit more points than needed because I want to have higher accuracy in the estimates. So the recommended choice will be 10 times the number of input features, but here I'm doing 20 times, so 160. And also I took some validation set points, some testing set points, just to show how the emulator is doing. Let's plot this space. So this is how the function is, the Sobol G star is according to the input features. Everything lives in 0, 1. This is the output. And this is how the space is distributed. This is a Latin hypercube, so pretty uniformly distributed in the 8D dimensional space. And everything, I didn't tell you, but everything is based on SALIP, which is the library I've been using lately, I think in the last year for doing GSA. I've just made it compatible with GPErks. And so now everything underneath works using SALIP, but making use of it in a different way, because now we have emulators and not deterministic functions. But still, you can use SALIP as out of the box when you have a deterministic function. So now we have a deterministic function because we have a deterministic function because, of course, we have this expression here, and we have it here. We have f, right? And f is taking as an input the x rows in the matrix X as before. So we still can use SALIP within GPErks in a very out-of-the-box manner. So we define the GSA object from the Sobol GSA class. And then we provide the dataset. So here, even if I'm not using the emulators, I want to provide the dataset just because the dataset contains information about the dimension of the problem, the bounds of the problem, and so forth. So I'm providing the dataset here as a constructor. This will be equal. Either we use the full model or we use the emulator. And then I provide the parameter n and the seed. Now the parameter n, maybe I might have written something about it, but basically the parameter n is the number of Monte Carlo points that we want to use to estimate the variance with using a variance decomposition approximations methods. In this case, we are using the Saltelli method for approximating these integrals. And this method indeed needs a number of points, which is basically n. And this is times plus 2. So basically, we will need n times 2d plus 2 model evaluations to estimate the Sobol indices for a problem of dimensions d. Now, according to n, as n grows, you increase the accuracy of these estimates, because these are numerically estimated integrals. So for a quadrature formula, if you increase the number of points, you increase the accuracy of the integral. But a wise choice is to take this value to be between 10 to the power of 2 to 10 to the power of 4. But just to be in the middle, we take 10 to the power of 3, so 1,000. Here I'm just using a power of 2 because otherwise Salib complains because it uses Sobol sampling underneath. But even if you plug in 1,000, it's the same. I can show you it works anyway. So the first thing I'm defining is this. And then what I'm doing here is to estimate Sobol indices, but using a simulator. So we provide F because we have F. So here, in a way, we are using Salib out of the box. And yeah, so this is the result of Salib. To show you that this actually matched to the, actually it's a bit tricky to go up. I did something more fancy where I use a different N. I use a different N basically ranging in a log space. So 10 to the power of 2, 10 to the power of 4. I'm increasing 10 and I'm showing you that the resulting indices are progressively better matching the analytical solutions. And you can see it here. This is the only printing the main effect. Remember, the main effect was 76, something like that, 0.76. You can see that initially it takes some time to adjust. For indices that are very low, for example, the last 4, it immediately converges to the analytical solution, but for higher magnitudes, it might take a bit. But in general, you can see that from 10 to the power of 3, with n equal to 1,000, we already get a pretty good convergence on the analytic solution. So that's why I'm always using n equal to 1,000 when I use Salib. In this case, when I use Saltelli method to estimate Sobol indices. So now, again, I just repeat it, but we are using the analytic function. So nothing new, because you could have done this by just using plain and pure Salib outside GPErks. But what I can do, I want to do now, is to emulate the G star function. So using this dataset, I want to emulate the data over the dataset that I've built. And I want to use the emulators to get the very same estimates. So, so here, we set everything as before. We set the device, we set the emulator, we set the optimizer, early stopper. So basically everything we saw before, we do exactly like out of the box and custom choices of this. We are emulating, it goes till the end, 3 restarts as always. You can see that the parameters now are 8. So we are in an 8-dimensional space. The score of, this is what is being printing here is always the score over the validation set, just to have a measure. But as I told you, computing scores on the val set is not meaningful, but we can plot how the training went. You see the GL kind of struggled, but then eventually he lost patience and he stopped here. The scores are pretty good, actually. And so we can also plot inference to see how it's going. I think this is emulating very well over the testing set that I provided here in the data set. There was also, a testing set provided. So 80 points. I think as a score over 80 points, this is pretty good. And we can trust this emulator. Actually, I plot also diagnostic to trust it more. The chi-squared is 100, but the expected was 80, so pretty good. And the uncorrelated values were already distributing in a good way around the 45 line, 45-degree line, sorry. And it's okay. I said, yeah, I can use this emulator to be used for GSA. It's pretty good. How do you use an emulator to calculate Sobol indices. So you provide n, still 1,000, because I think it's a good choice, and I showed you why. And also, and then what I do, instead of estimating using the simulator, I just estimate Sobol indices using the emulator. So what you need to pass, instead of f, this time you need to pass the emulator, of course, but now you need to pass also this, which is the number of samples you want to draw from the posterior distribution. So this is very important, because when you estimate the Sobol index, you can do it using a simple pointwise estimate, which is given by the mean of the posterior distribution. But if you want to take into account the fact that your function that you are using to estimate the indices is not a deterministic function anymore, but it's an emulator, you want to make sure that you take into account the uncertainty while making predictions of the indices. And so, yeah, I might have run this while talking because it takes a bit. So basically what this does is to, maybe 1,000 is a lot, but anyway, you repeat what Salib does with an analytic function, but you use the predict function of the emulator underneath, and you do it 1,000 times. So you say, okay, for 1,000, for the space suggested by Salib, where to evaluate Sobol indices, you take the emulator, you draw samples from the posterior distribution evaluated at those points, and you do it many times, such that eventually you don't get a single value of the Sobol index, but you get an entire distribution of the index itself. So, of course, when you plot summary, these distributions will be considered, the mean of the distribution will be plotted as a result. Yeah. Okay. This can take a bit, or maybe not. I don't remember. I think 1,000 was a fair number to show. Of course, as the number increases, the distribution becomes more defined in a way that if you just have 3 random samples from the posterior distribution, these 3 samples might be very far from the mean. So in that case, if you want to use these end rows to be very low, you can directly use the mean of the emulator directly. Actually, I think there's no function that does it. I should provide a function that only uses the mean of the emulator if you don't want to do draws from the posterior distribution. Yeah, sorry about that. If you have questions in the meantime that this runs, it's a good moment. Okay, so we got the mean of the distributions of the Sobol indices. They are not perfect. You see, that was 60, that should be 60, 76, something like that. But we can plot to see how they are distributing according to the absolute values. You can see here how distributions of Sobol indices are. The analytic solution was the red one. When you go very low, of course, these are difficult to discern, but I guess here there is something a bit odd in the sense that this should decrease consistently. But I think overall, this kind of GSA result is pretty consistent to the analytic solution. For second order, yeah, we also matched the first one. The others are very small. So for second order effects, it's even more difficult because it's double the error when you evaluate the integrals to estimate this. And plus you're using an emulator, so another an extra level of uncertainty as well. What I want to show you is that you can actually correct these distributions to neglect effects that you think are negligible. So how do you neglect this? You just put a threshold. For example, I say if, or maybe I can plot this separately. Let's create something here to show you what I'm talking about. So if you select this, we are cutting everything which is below 0.1. Actually, we should do 0.2 to make something disappear. No, actually, I want to just remove these guys here. No, let's put 5. I don't know. But if you do like this, you say, okay, for me, some effects are negligible, and so you can plot them using actually the box plot, which is given by the plot without any flag. But also I can provide different ways of plotting this, and I'll show you later. So this is what we just saw, but we have said, okay, these index are negligible, and so I put them all to 0. And the threshold here is enforced actually not on the mean value, but I've asked that the lower quartile is above the threshold. So these are distributions. I want that the lower quartile is above the 0.5. If it's not, I just bring down to 0 the distribution. And this process has to be done, and also the selection of a representative, in this case, will be the mean or the median. This has to be done because if we want to plot, for example, donut charts, stuff like that, we need to have a mean value of the indices. And so this is many ways of plotting the same thing. Donut charts is just showing you the effect, the first order effect given by the color. Actually, these colors are not the best because when you increase the dimension, I should use a cycling color scheme and not the variance of blue, because otherwise you don't really see it. But I mean, these are the first two. These are the most meaningful. Sorry, the first two, x1, x2. And then what you can do, you can subtract from the total effects, you can subtract the S1 such that you can also plot the higher order interactions. So these higher order interactions will be from the second order up to the whatever order. And it's a good representation here to have, just to have an idea of how big are the higher order effects. And also, this is what I call a fancy donut, because this shows, basically, this shows S1 and S2 all together. So what you have in the outer part is the summation of first order and second order. Inside, you see with different variants of the same color, you see the splitting. So the biggest part is the first order effect, and the small part is the second order effect. And the same for the second parameter. Second parameter has a first plus second order, which is the outer color, and the inner color is going to be the first order. So basically this part here is the first order, and then the second order is something that I'm not plotting. And again, this is the higher order interaction. So if you plot, in a way, if you plot only this one, you have immediately an idea of how big is the first order, how big is first and second order in total, and how big are the higher order interactions. Of course, here I had to make sure that I'm not plotting twice the same thing. So if x1 has a second order effect with x2, I'm not adding the same value here, but I'm making sure that I split that second order equally into all the parameters that appear in the pairs of interacting parameters. So in this case, x1 only has an effect with x2. So I divided the second order effect in two to be plotted equally in these two guys. And then we have an heat map kind of plotting, which I think is useful as well. This shows variation from 0 to 1. Of course, 1 is the highest you can reach, both of S1, ST. And eventually, I also have a network plot. This is pretty unlucky because it doesn't really show what's going on here. I might use something. Sorry, I might take something from a paper just to show you what the plot is. Yeah, so the network plots can be like this. So basically, what you have is a very nice representation of both first, second, and higher order interaction terms. So the outer node is colored in the darkest blue. It represents the total effect. Then if you see a light node, means that this is the first order effect. and actually the border is the total effect. So you have total with the first order printed inside, but sometimes the total overlaps with the first order or almost there. There is a very light corner around it. Sometimes you only have total effect, but not first order. And then the thickness of the linking line is the second order effect. So you can see, for example, some lines are more thick, less thick. Some have very big first order effect. First order effect, and some, first order effect here, total effect dark, and first order effect is the first order. So this is, for example, CA50 parameter, and you can see that it has both a total and the first, which are pretty big. Some of them have only first order, total effect is overlapped. You can have many things, and these networks makes you understand the contribution of parameters, because all is scaled to match the sides. So all the sides are normalized to be consistent between themselves. Yeah, so this was pretty unlucky because I just had one interaction and didn't really show the power of the plotting strategy. Yeah, so this is pretty much it.